From the moment people realized how infinitely great the cosmos is, they have been asking themselves the same question. Are they alone in the universe? Is there a different, unfamiliar life on the surface of distant worlds which are unreachable for us in the icy abyss? For many years, scientists have searched fruitlessly for answers to these baffling questions. Eventually, giant telescopes directed their gaze up at the sky, and spacecraft left our planet to head for other worlds, and so it is time for us to trace the path of amazing discoveries and lift the veil of mystery over one of the most important questions of today's science. The first destination on our journey will be the silent, barren Mars, which will appear to us from an unexpected angle. Then we'll travel to the cold, misty Titan to descend into its amazing methane lakes, which may be the cradle of strange, exotic life. Instantly covering several light years, we'll reach Alpha Centauri, the closest star to the Sun, and one of the most important objects of scientific research. Our next stop will be an amazing exoplanet called Teegarden B, one of the most Earth-like celestial bodies in the universe. And last but not least, we will visit several other potentially habitable worlds that demonstrate an amazing variety of natural conditions on their surface. Let's get ready, and we begin. Cosmo. This is Mars. That's what it is believed to look like several billion years ago. Heat and liquid were trapped within the dense CO2 atmosphere the planet was shrouded in. Numerous rivers used to flow on its surface, and most of its northern hemisphere used to be covered by water. However, all this was to vanish, leaving behind only traces on rocks. It is thought that the weak and unstable magnetic field of Mars failed to protect it against solar wind. In hundreds of millions of years that followed, its atmosphere gradually deteriorated, with water vapor breaking down into hydrogen and oxygen. The lighter gas rose up into the upper layers of the atmosphere to float away into space. As for oxygen, it reacted with rocks, which gradually led to the planet getting tarnished by rust and sand. A thin layer of orange dust and perpetually frozen ground. That is all that remains of the great abundance of water on the red planet. To have a better understanding of what is currently going on Mars, we will first have to look in its depths. Thanks to the sensitive seismographs on board the InSight probe, which have been exploring the inner makeup of the celestial body for 4 long years, scientists have some ideas about the processes running in the planet's depths. At the very center of the planet, we can observe a large and massive core of iron, sulfur and nickel. Its radius is more than half the size of the entire celestial body, and its temperature lies between 1800 and 2000 Kelvin. Because of the enormous pressure, most of the core is in a solid state, and therefore incapable of producing a stable magnetic field. The core of the planet, in its turn, is surrounded by a layer of molten mantle about 1,500 kilometers thick. Its composition is heterogeneous and depends on its depth. The lower layers contain various metal oxides, while the upper ones are composed of olivine and silicates. On the outside, the mantle is bound by a massive crust, the average depth of which is estimated to be about 50 kilometers. This is 5 to 10 times greater than the parameters of our planet's oceanic lithosphere, and comparable with the thickness of the Earth's continents. It is also noteworthy that in the northern hemisphere, the Martian crust consists predominantly of andesite, and in the southern hemisphere of basalt, which may indicate that it was formed at different times. Decades of observation have yielded hundreds of thousands of images of the surface of Mars. By putting these together, scientists have been able to produce an incredibly accurate and detailed map of the celestial body, containing many objects. Some of them are quite small, while others stretch for thousands of kilometers and can be seen with telescopes even from Earth. And one such region of interest is Valles Marineris. This gigantic system of intertwining canyons and chasms stretches along the planet's equator for 4,500 kilometers. Its western part is deeply cut by the immense volcanic Tharsis Plateau, and our plunge into the Great Rift will begin almost in the center of the giant plateau. It is here that the unique and mysterious region, marked on maps as Noctis Labyrinthus or the Labyrinth of Night, is located. It is an area of chaotic terrain, stretching 1,200 kilometers from west to east. Here, numerous deep, steep-edged drifts intersect multiple times, dividing the surface of the planet into irregularly shaped blocks. The top is made up of softer, lighter sediment, heavily eroded, while the base is made up of solid bedrock. Over billions of years, the slopes of the chasms have collapsed in many places, leaving behind numerous landslides. It is thought that it was here that precipitation that fell on the surface of the upland regions in ancient times accumulated together and flowed eastwards in unstoppable turbulent streams. Evidence of this can be seen in the traces of deep water erosion, seen at the bottom of most chasms, and in the layered structure of slopes and landslides. In addition, spectral analysis shows that certain minerals that require liquid water to form, such as hematite, opals and dian sulfates, for example, are abundant in this region. Observations show that Noctis Labyrinthus is periodically obscured by dense fog, meaning that it is still one of the most humid regions on the planet. It is thought that the water contained in the soil evaporates into the thin Martian atmosphere during the day, and the high walls of the gorges prevent the humid air from dissipating. With temperature dropping, the water condenses as microscopic ice crystals that slowly settle on the surface, forming a thin layer of frost. As one moves eastward, the bizarre interlocking chasms of Noctis Labyrinthus gradually morph into a system of giant canyons that occasionally intersect. Over billions of years, powerful streams of water dug deep channels in the Martian rocks, and then winds and sandstorms ate away at their slopes. But whichever path we take, it will eventually lead us to the giant Coprites Chasma. It is here that the deepest point of the Valles Marineris is recorded. It lies 11 kilometers below the surrounding plateaus. Calculations show that in ancient times, Coprites Chasma was a narrow and long running water lake, which when at its fullest was comparable in volume to the Earth's Black Sea. The region is believed to be one of the most promising objects for future research. The soil at the bottom may contain traces of ancient microorganisms, and its slopes are quite literally recorded pages of the geological history of the planet, and are of great scientific value. As we continue along the canyon, we find that it gradually loses its steepness and gently dissolves into the giant Chrysoplanitia. Here too, however, we see traces of the water element in the form of rounded terraces and elongated islands, probably formed by sediment from Valles Marineris. Similar geological formations can be found on our planet in the deltas of major rivers, such as the Amazon and the Nile. Thus we have made acquaintance of one of the most tremendous and visible evidences of there having been water in the ancient eras of Martian history. However, the giant Valles Marineris rift has only been explored from space. The wheels of a Mars rover have never touched it. to get a closer look at the red planet, we will have to travel far to the east. After flying several thousand kilometers over unfriendly rocky deserts, we finally reach a large crater called Gale. About 3.8 billion years ago, a massive asteroid collapsed here, leaving a deep circular depression 154 kilometers across. At its center there is Mount Sharp, a vast irregular upland area composed of layers of sediment. In ancient times there may have been a large circular lake with a central island. In the present day, however, Gale Crater is known as the landing area for the Curiosity rover. The story of this mission began almost 11 years ago when the Curiosity autonomous probe landed on the surface of Mars on the 6th of August 2012, a symbol of human determination and thirst for knowledge. The mission's goals included studying the planet's climate and relief, as well as searching for water and traces of biological life. Almost immediately after landing, the rover found evidence that the planet used to be much wetter in the past than it is now. The first photos transmitted to Earth clearly show a valley washed away by a torrent of water. The area has been dubbed Peace Valleys, meaning the Valley of Peace, and is one of the clearest instances of evidence of water erosion on the planet. Curiosity then headed east and soon reached a sandpit called Rock Nest. Here it took its first soil sample and found it contained around 3% of water. Next, the rover turned southwest and continued on its way. It crossed the rocky wastelands of the Glenelg region, where ruthless winds had crushed sediment down to bedrock formed more than 4 billion years ago. Then, climbing occasionally up rocky slopes, Curiosity reached the western end of the Bagnall Dunes, studying the sedimentary rocks, which are relatively recent in geological terms. From the desert, the rover turned south and set out on a long and tiring climb up the slope of a small mountain range called Vera Rubin. Along the way, the sand and silica under its wheels gave way to hematite, an iron oxide that only forms when in contact with liquid water. It turns out that the mountain range is largely made up of this substance, which means that in earlier times, the climate in this region was much more humid. In total, Curiosity stayed on Mars for more than 3,000 days, roughly 5 times the planned duration of its mission. Despite all the difficulties and obstacles, it traveled nearly 30 kilometers across the harsh Martian terrain and took 28 samples of alien soil. The probe's chemical analyses detected not only water, but also organic molecules including benzene and aromatic hydrocarbons, while its cameras beamed back to us thousands of photos and videos. Leaving the tenacious Mars rover behind, we will continue our journey and head southwest. Here, Hellas Planitia is one of the largest impact craters on Mars. It is thought that about 4 billion years ago, a massive asteroid with a radius of about 50 kilometers crashed into the planet here at high speed. The terrific explosion left behind a gigantic crater about 2,300 kilometers in size, and millions of tons of rock were crushed and ejected far beyond its limits. Some of these fragments may have reached outer space and then crashed to the planet's surface hundreds or thousands of kilometers away from the site of the cataclysm. It should be noted that at that time, Mars was likely to have been a friendlier and more favorable celestial body than it is now. The giant lowland area that appeared at the impact site was quickly filled with water, forming a large lake or a drainless inland sea. Over billions of years, it gradually shallowed and became what we see today. A huge crater, more than 7 kilometers deep. From a distance, the bottom of the basin may look smooth and flat, but this is just an illusion. In fact, it is covered with numerous small hills and fractures whose appearance is largely accounted for by the movement of layers of subterranean ice. Similar relief occurs on Earth, in Arctic barren expanses and permafrost zones. Due to its great depth, the atmospheric pressure in this region is about twice as high as the global average, resulting in unusual weather phenomena. For instance, from time to time, a misty haze forms over the crater, which is uncharacteristic of Mars. The wind carries some of the mist out of the crater, but its wisps quickly disperse in the thin atmosphere or settle on the frozen rocks. During Martian winter, the Hellas Planitia is entirely covered with frost and when seen from the Earth, appears as a large bright spot. Because of this, the area has long been mistakenly considered an upland, and it wasn't until the end of last century that its true nature was determined. Next, our route takes us to the north, to Jezero crater, which used to be a large running water lake in the past. The Sava River flowed into it from the north and the Neretva River from the west. Traces of these large water arteries are still to be seen on the surface of Mars. These appear as layered deposits of fluvial sediment and large scour marks on the mountainous walls. It was one of these regions that became the priority target of the Perseverance rover, which descended into Jezero crater on the 18th of February 2021. Originally, the rover was planned to land near the Three Forks area, in the Neretva River Valley. However, weather conditions shifted the landing point 1.7 kilometers to the southeast, and the rover was separated from its target by an area of impassable sand called Sator. It was at this point that the unique Ingenuity helicopter got to show its worth. It flew over the surface of the planet and provided a wide-angle panorama of the ancient delta, as well as a unique photo of the Kodiak Plateau, 2.3 kilometers from the rover's landing point. Once the rover had settled in and reconnoitered its surroundings, it started out on a long, arduous journey around the unfriendly desert that separated it from its destination. Traveling south along the very edge of Sator, the rover stopped from time to time to collect soil samples. At the same time, Ingenuity successfully completed flight after flight, beaming back to us many photos of Mars from previously inaccessible angles. On Mars Day 168, the spacecraft turned westward. The idea was to pass along the bottom of the crater, skirt the southern tip of Sator, and reach a rocky ridge along which it would head north towards the delta. However, the terrain proved difficult and the rover was forced to turn back. Pretty much retracing its way back to the landing area, Perseverance set off towards its destination. After smoothly skirting the northern part of the desert, it gradually turned westwards. Eventually, after a long and arduous journey, the rover did reach the delta and began exploring it. This occurred in April 2022, 413 Martian days after it had landed. By now, Perseverance has traveled more than 18 kilometers across the unfriendly Martian desert. It has collected 15 soil samples and sent more than 166,000 images as well as gigabytes of data from various sensors. In addition, the MOXIE vehicle, which is part of the rover's science payload, successfully obtained about 100 grams of oxygen from the Martian atmosphere's carbon dioxide, which seems to reveal prospects for future colonization of the planet. At the same time, Perseverance's seismographs recorded several Mars quakes, enabling scientists to learn more about the internal structure of the celestial body. The Ingenuity helicopter proved just as useful. It has completed more than 50 flights by now, traveling a total of over 8 kilometers, thus convincingly proving that even in the rarefied atmosphere of Mars, it is possible to use aircraft for research and exploration. In addition to desert landscapes and rocky debris, Perseverance occasionally photographs the night sky of Mars. For example, this little white dot here is one of its satellites, Deimos. More recently, Perseverance captured Phobos briefly eclipsing the Sun. This unique observation was not just a spectacular sight, but it also provided astronomers with a wealth of important data. Unlike our planet, Mars has two satellites, which are very small, irregularly shaped celestial bodies. Observations and spectral analysis suggest that Phobos and Deimos are similar in composition to carbonaceous asteroids, but their exact origins are still a subject of scientific debate. One hypothesis claims that they are the remnants of a small celestial body captured by Mars from the main asteroid belt several billion years ago. The tidal forces of the planet probably tore the object into many fragments, and Phobos and Deimos are the largest of them all. According to another hypothesis, a large protoplanet allegedly collided with young Mars at the dawn of the solar system's formation. As a result of this cataclysm, some of the fragments were thrown into space, where gravitation shaped them into two rather large objects. Phobos is the larger of the satellites. It orbits the planet above the equator at an altitude of about 6,000 kilometers, which is about 64 times less than the distance from the Moon to the Earth. Incidentally, some man-made satellites above our Earth drift 3 to 5 times higher than this celestial body. However, Phobos is so modest in size that when observed from the surface of Mars, it appears 3 times smaller than our Moon to us, even at this distance. Another surprising fact is that Phobos has an extremely low average density, approximately 1.9 grams per cubic centimeter. This means that up to 40% of its volume must be hollow. It is possible that this object, like some asteroids in our system, consists of several pieces of debris held together by gravity alone. Due to tidal forces, Phobos is gradually losing height, about 1.8 meters per century. It is estimated that in 10–11 million years, it will be crushed by the pull of Mars into many fragments, and that after another 33 million years, they will finally collapse onto the surface of the red planet. By that time, Mars will be likely to lose its second satellite, Deimos. Currently, this celestial body is moving in a circular orbit with a radius of about 23,500 kilometers, but this distance is gradually increasing. Calculations show that in a few million years, the satellite will finally leave the gravitational influence of Mars and float in space quite independently. Deimos is a very dark object because its surface absorbs almost 93% of the light shed on it. The satellite's small size means that its disk cannot be seen from Mars with the naked eye. Deimos appears to the observer as a pinpoint source of light, even though quite bright. Its orbit makes it appear to drift across the Martian sky towards Phobos, but this is just an illusion. In fact, both satellites orbit Mars in the same direction. Titan is located about 10 astronomical units from the Sun and is outside the habitable zone of our star. It is Saturn's largest satellite, and its orbit lies well outside the Great Rings, at a distance of about 1,200,000 kilometers from the center of the planet. The trajectory of the celestial body is close to circular, and a complete orbit around the gas giant takes a little less than 16 Earth days. Titan's diameter is 5,152 kilometers, which is 5.6% larger than that of Mercury. At the same time, the mass of the celestial body is relatively small at only 1.35 times 10 to the power of 23 kilograms, which is about 40% of Mercury's. Calculations show that the satellite's average density is about 3 times less than that of the Earth, which means it has a completely different chemical composition. According to contemporary concepts, Titan has a massive core at its center, about 3,400 kilometers in diameter and made up of various silicon compounds. It is surrounded by a thick layer of densely packed ice, which is at the bottom of a cold liquid ocean hundreds of kilometers deep. The ocean, in its turn, contains large amounts of dissolved ammonia, methane and various caustic salts, so that its freezing point is markedly lower than that of ordinary water. For this reason, Titan's subsurface ocean remains liquid even in sub-zero temperatures. It is bound by a thick crust around 100 kilometers thick, consisting of a mixture of water ice and methane hydrate. The tidal forces of the nearby Saturn are continuously deforming it, causing massive rifts and fractures. This causes large cryovolcanoes to form, ejecting great quantities of methane, ammonia and water onto the surface of the celestial body. Methane plays about the same role in Titan's atmosphere as water vapor on Earth. The fact is that the average surface temperature of the satellite is only about 94 Kelvin or 179 degrees Celsius below zero, which is slightly below its boiling point. Natural variations in this parameter cause hydrocarbon vapors to condense and precipitate, forming methane seas, lakes and rivers. Titan's atmosphere is composed mainly of hydrogen, which makes up about 98.4% of its volume, while methane accounts for about 1.6%. Due to its extremely low temperature, the satellite's atmosphere remains condensed near its surface, and the ring of the mountains surrounding it is less than 500 meters high. Most of the surface of the celestial body is permanently obscured from our eyes by multi-layered clouds and an orange-yellow tholin haze. This unique weather phenomenon is a fog formed by tiny droplets of liquid methane and dissolved organic matter, which gives Titan its characteristic hue. This haze pervades Titan's surface, absorbing and scattering visible light but transmitting infrared light. This peculiarity leads to an unusual anti-greenhouse effect, which cools the satellite's surface by roughly another 10 degrees. This effect makes Titan difficult to explore, but thanks to the Cassini's orbiter's infrared cameras, Titan was in parts mapped out earlier this century. Of course, it is not as accurate as we would prefer, but even this much is enough to outline the most striking features of the celestial body's surface. The face of Saturn's largest moon is full of contrasting spots. Some of these reflect most of the light that falls on them, while others are relatively dark in color. One such area is slightly south of the equator and is called Aztlan. One of Titan's highest mountains, Mount Doom or Doom Mons, is located here, towering about 1.5 kilometers above the surrounding plains. The whole mountain reaches up to 60 kilometers in diameter. Its summits are craters, and its slopes have relatively fresh traces of turbulent flows. This may suggest that Doom Mons is an active cryovolcano. To the northeast from it is Titan's deepest depression, called Sotra-Patra. It is a giant depression about 30 kilometers long, the bottom of which is located about 2 kilometers below the adjacent plains. It is thought to be the mouth of a huge cryovolcano, and is part of a single tectonic structure along with Doom Mons located close by. To the north of Doom Mons, there stretches the immense Mahini Fluctus, a vast area covered by Doom Mons' ejections. The area extends for about 180 kilometers and varies in width from 15 kilometers in the south to 60 kilometers in the north, where torrents of frozen material alternate with expansive fields of sand dunes consisting of a mixture of frozen methane and water ice. Our flight will continue over the dark area of Fensel. The largest impact crater of the celestial body, Minerva, is located in its northwestern part. It reaches 440 kilometers in diameter, which is about 3 times larger than any other crater on Titan. The depression is about 200 meters deep, and the ring of the mountains surrounding it is less than 500 meters high. The fact is that according to studies, Minerva is not only the largest, but also the oldest extant crater on Titan. Different estimates put the age of the crater at between 300 million and 1.2 billion years. Erosion and tectonic processes have severely damaged the crater, and it is only thanks to its sheer size that it is still visible. Minerva has a well-defined internal structure. At its center there is a small flat plain, surrounded by a ring of hills. This region, with a total diameter of about 200 kilometers, is rather light and clearly visible from space. It is surrounded by a so-called moat, a stretch of dark plains about 50 kilometers wide. This is followed by a ring of low mountains that form the outer boundary of the crater. Our flight next takes us to the south. Here is one of Titan's most impressive and mysterious landmarks, Hautei Arcus. This is a unique formation in the solar system and is a bright arc-shaped region about 600 kilometers long. Radar data from Cassini shows that Hautei Arcus is a natural boundary between the Rocky Mountains in the northeast and a wide valley in the northwest. It is also noteworthy that some parts of this area change color from time to time. This phenomenon is thought to be linked to the eruptions of cryovolcanoes, whose emissions cover the surface of the satellite in a thin layer and then flow into a nearby valley or evaporate into the atmosphere. From space, one can clearly see light channels similar to riverbeds running from the mountains of the Hautei Regio to the northwest. This is where Xanadu is located, which is a vast lowland area with highly rugged terrain. Its northwest boundary is formed by Mithrim Montes, which are 3 parallel ridges stretching for about 150 kilometers, with an average height of 1.9 kilometers. Among the peaks of the southern range is the highest peak on Titan, reaching 3,337 meters. Standing on top of it and looking west, you can see a vast dark plain stretching several hundred kilometers in front of you. It is called Shangri-La, and it is thought that this whole area used to be flooded with liquid methane. It is assumed that it may have persisted beneath the topsoil, similar to the Earth's underground water. Most of this region is below average elevation and has a comparatively flat terrain, but lighter hills can be seen in some places. In the past, these may have been islands in the middle of a hydrocarbon sea. To the west of Shangri-La is the bright Adiri upland area, clearly visible against dark regions around it. The area extends for up to 2,500 kilometers and is a veritable network of numerous drainage canals and caves clearly visible in the photographs. These are thought to have been formed by abundant flows of liquid hydrocarbons. To the west of Adiri is the vast dark lowland area of Belet, and to the east, near the border with Shangri-La, is the Huygens landing site, so far the only vehicle that got to touch down on the surface of an object in the outer solar system. The descent probe was part of a science program called Cassini-Huygens. Together with the Cassini automatic probe, it left Earth in 1997 to spend 7 years in interplanetary space. The spacecraft entered the orbit of Saturn only in 2004, and in early 2005, Huygens reached Titan and plunged into its atmosphere towards new discoveries. Cassini, on the other hand, remained in orbit around the gas giant to carry out its part of the research program, as well as to continue serving as a transponder for the lander. The probe spent just under 2.5 hours in the atmosphere, gradually dropping speed using a sophisticated parachute system. Eventually, by the time it touched down on the surface, its speed was 4.4 meters per second. The probe successfully withstood a momentary 15-fold overload and soon went on to collect information. Huygens was equipped with a vast array of scientific instruments, most of which were designed to study different aspects of the satellite's atmosphere. The probe used them to measure the strength and direction of air currents, as well as the electrical conductivity, temperature and composition of the atmosphere. The probe also took photographs and made audio recordings, and on landing, it examined the composition and properties of the ground. The first thing the cameras saw after making contact with the surface was a flat plain, dotted with rounded rocks of various sizes, the shape of which clearly indicated the impact of powerful fluid currents. A special drill was also used to sample the surface, penetrating 15 centimeters into the ground, while multiple sensors measured its density, texture and composition. It turned out that a thin layer of small rounded pebbles lay on a relatively soft but dense substrate, similar in consistency to wet sand or dense snow. Also, methane gas was released during the drilling process. The ground at the Huygens landing site is believed to have been like sea sand, saturated with liquid hydrocarbons. In total, the probe transmitted around 500 megabytes of information to Earth, including 350 photographs. Further careful analysis revealed several unique features of the celestial body related to its atmosphere. For example, it turned out that at an altitude of about 80 kilometers there is a layer of almost complete calm, as if separating Titan's atmosphere into two parts. Neither air currents of the upper atmosphere nor winds of the surface reach this layer. What caused this phenomenon is not yet known. Another feature is that Titan has two ionospheres. The first of these is located at an altitude of about 1,200 kilometers. It is a layer of heightened electrical conductivity with a large concentration of ionized particles. This layer is known to be formed by stellar wind streams and cosmic radiation. The second ionosphere lies much lower, at an altitude of about 60 kilometers, and the reason for its formation is still debatable. Moving northwest from the Adiri area, we reach Titan's largest hydrocarbon reservoir, the Kraken Mare. Its total area reaches 400,000 square kilometers, which is slightly smaller than the Black Sea. Due to the high viscosity of the liquid hydrocarbon mixture, it has not yet been possible to measure the exact depth of the reservoir. It is only known that in most of the area, it is over 200 meters. Another large natural basin, the Ligeia Mare, is located slightly to the north, near Titan's pole. Its diameter reaches 500 kilometers, and its area is about 100,000 square kilometers, which is about 3 times larger than Lake Baikal. The seas are connected to each other by the narrow and long Treves Fretum, 173 kilometers long. Also in the subpolar region, there are many smaller lakes and lagoons filled with liquid methane. In 2014, analysis of earlier images beamed back by Cassini revealed a large bright object on the surface of the Ligeia Mare. On comparing photographs taken at different times, it was established that within a few months the mysterious object had grown to 260 kilometers in diameter, to disappear almost instantly without a trace. Several hypotheses have been put forward to explain it. According to one of them, temperature differences lead to a constant stirring of layers of liquid hydrocarbon mixture in the Ligeia Mare. This causes nitrogen bubbles to form and rise to the surface from the depths of the reservoir, and thus form large clusters of persistent shiny foam. Due to the high viscosity of the hydrocarbons, such bubbles can reach 4.5 centimeters in diameter and remain stable for months. From space, these structures resemble large islands because they reflect infrared radiation well. Such bubbles would have been a significant hindrance to the operation of a submersible probe, which was scheduled to be launched to Titan back in 2010. However, the mission was postponed indefinitely for various reasons. A higher priority was given to the Dragonfly program, which NASA is working on now. The vehicle is currently in the design phase and has just recently passed key tests of its blades. The launch from Earth is scheduled for 2027. As conceived by its creators, Dragonfly will be an octocopter, an aircraft with 4 twin propellers. This design will allow it to stay in the air even if it loses several blades, unlike its predecessor, the Ingenuity Mars helicopter. A radioisotope thermogenerator, powerful enough to enable the vehicle to climb to a height of 4 kilometers and travel at a speed of about 36 kilometers per hour, will be used as the power source. The scientific capabilities of the probe are also impressive. It will be equipped with a versatile camera capable of producing both panoramic photographs of the surrounding terrain and macro images of the ground. At the same time, the mass spectrometer will make it possible to determine the chemical composition of atmospheric samples and the internal structure of rocks. Perhaps Dragonfly's data will help us clarify an important question. Do we at least have a chance of encountering primitive life? The possibility of life on Titan remains hotly debated. On the one hand, the extremely low surface temperature, the presence of extremely toxic hydrocyanic acid in the atmosphere, and the absence of liquid water would likely rule out the presence of biological life as we know it. Titan's atmosphere, on the other hand, exhibits an incredible diversity of organic compounds. Nitrogenous bases and amino acids, which are the building blocks of proteins, RNA and DNA, could be naturally synthesized on its surface. It is also known that liquid methane can serve as a solvent and potentially play the role of water in biochemical reactions. In addition, experiments show that under certain conditions, a mixture of liquid hydrocarbons with phosphine forms an environment similar to the primordial soup of the early Earth. This means there's a chance of encountering downright exotic forms of life on the surface of the satellite. The Earth has been emitting structured radio signals into space for around 100 years now. The radio noise from the Earth reached dozens of other stellar systems long ago, including Arcturus, lying 37 light-years away from us, and Aldebaran, which is roughly 65 light-years away. Besides, our radio signals may be heard on the surfaces of a great number of potentially habitable exoplanets, like Ross 128b or Gliese 667cc. Still, the triple stellar system of Alpha Centauri remains the closest neighbor of the Sun, which automatically makes it the first obvious candidate for the destination of the first ever interstellar flight. Alpha Centauri is known to be a multiple stellar system made up of 3 components. 2 of the larger ones are relatively close to each other. Seen with the naked eye, they appear to be a single source of light. The 2 components follow a slightly elongated orbit around the common mass center, which takes around 80 years to complete. The maximal distance between the stars may reach 35 astronomical units, with the minimal distance reaching 11.2 astronomical units. As for the distance between these objects and the Sun, it is reportedly 4.36 light-years. The most massive, the largest and the brightest component in the system is dubbed Alpha Centauri A. This is a main sequence star with a mass of about 108% that of the Sun. Its radius is reportedly 1.22 times that of our Sun. Even though the surface temperature and the spectral class of Alpha Centauri A are close to those of our star, it emits 1.5 times as much energy. There are no confirmed exoplanets in the environs of this star. However, while the star was being observed in the infrared in 2021, some evidence was found of there being a planet-like object close by. According to preliminary estimates, its mass may be anything from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet. 1.1 astronomical units away from its parent star, the hypothetical celestial body completes a full orbit around it within roughly a year. Additional observations are called for to verify the data, which can be done with the help of either the James Webb Telescope or else Earth-based observatories. The second component of the system is called Alpha Centauri B, or Ptolemy, and it also falls into the class of main sequence stars. However, its mass is 10% less than that of the Sun, and its radius measures only 86% or so that of the Sun. Ptolemy is also slightly cooler than our star. Its surface temperature is reportedly 5260 Kelvin, or slightly lower than 5000 degrees Celsius. With these factors combined, the celestial object has an orange hue, and its luminosity is on average twice as low as that of our Sun. Incidentally, Alpha Centauri B emits a lot more energy in the X-ray range compared with other objects of its class. Besides, the star is peculiar for its temper, and there are bright flares and ejections to be seen on its surface. No confirmed exoplanets have been detected near this star either. In 2012, a group of astronomers from the Geneva Observatory put forward a suggestion that there was a planet very close to it, whose orbital period was around 12 days, and whose radius measured slightly less than that of the Earth. The suggestion was made based on 4 years of observation of the star's proper motion. However, 3 years later, a mathematical error was detected to have been made in the course of data processing, and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first two. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it its name, Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its low luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units or 0.21 light-years, but in the next 300,000 years it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts 2 confirmed exoplanets, as well as at least 1 hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects, like asteroids or comets. The first planet in the system, Proxima Centauri B, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri B gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin, or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet. As the celestial body is extremely close to its host star, however, it is likely to be tidally locked, so it faces the star with one and the same side. A dense atmosphere could compensate for sharp contrasts in temperatures, which are inevitable in such conditions, but just like any other red dwarfs, Proxima Centauri is often seen to eject stellar matter. Also, ionizing radiation flares are observed. It is assumed that such activity gradually destroys the atmosphere of the closest objects. A powerful magnetic field that could be encompassing Proxima Centauri b could offer some protection against the destructive process, but chances that there is any magnetic field there are thin. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of mini-Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth. If it does exist, and if this isn't another measurement error, a year on this planet lasts about 5 Earth days, and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether this space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now. But the 40 trillion kilometers of space vacuum between us are too overwhelming for us to cover at this point. It takes light over 4 years to get there, but for humans such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of this century. They will not measure over a centimeter in size, and special thin and durable sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by impulses of a highly powerful Earth-based laser. Estimates show that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. Before we set out on a space journey beyond the boundaries of our system, we have to decide on the manner of selecting a planet that resembles the Earth most from thousands of candidates. What should be the parameters of this fascinating world, and what should we take into consideration first? It goes without saying that planets favorable for the genesis and sustenance of life have always posed considerable interest to scientists. However, it is no easy matter to single out suitable celestial bodies among a great number of those discovered by now. To have clear-cut selection criteria, scientists worked out the so-called Earth Similarity Index, or ESI for short. It is based on several principal parameters: a planet's radius, density, and average surface temperature. This combination makes it possible to calculate the object's mass, approximately estimate its chemical composition, gravitational level, whether or not there is an atmosphere, and if there is, analyze some of its characteristics. It also helps establish if there is liquid water on the planet's surface and other information. The standard of this index is the Earth, with its parameters assumed as ideal and its ESI equaling 1. Based on the Earth Similarity Index, all the objects known to us conventionally fall into 3 categories. The first one is objects whose ESI is under 0.5. These are for the most part gas and ice giants, as well as extremely hot or, on the contrary, cold objects. This is the category most of the solar system planets and satellites fall into. It takes just one characteristic to greatly exceed the maximum permissible values for a celestial object to be unfavorable for the genesis and sustenance of life. Let's take Venus, for instance. The radius and mass of this celestial body are very close to those of the Earth. However, due to its close proximity to the Sun and a dense atmosphere, its surface temperature is extremely high. That is why, in spite of a close similarity to the Earth on the face of it, Venus's ESI is not high, at just 0.44. Of course, there being any life on its surface is totally out of the question. Celestial objects whose ESI is within 0.5 to 0.7 fall into the second category. These objects resemble our home planet noticeably more. They're mostly rocky worlds with relatively moderate temperatures, but it can also be ocean planets and even some large satellites. Incidentally, a high Earth similarity index per se does not warrant favorable conditions for life. For example, quite often low-mass planets are incapable of retaining a dense enough atmosphere, while their magnetic field is too weak to protect the surface from lethally dangerous radiation. Other celestial bodies yet may happen to be located too close to their parent star and so get tidally locked. Of course, all these factors greatly reduce the chances of life's genesis and sustenance. As for the third category, it contains celestial bodies with a high ESI, that is over 0.7. All of these planets are beyond the solar system. According to estimates, the size of these worlds and the conditions on their surfaces are potentially close to those of the Earth. Among these planets, there is one which resembles ours most, and it lies just 12.5 light-years away from the Earth. This amazing world orbits Teegarden star, a small red dwarf discovered in 2003. This star is 1,370 times dimmer than the Sun. This means that it cannot be observed with the naked eye, even though it lies quite close to the Earth. The mass of this tiny star is roughly 9% that of the Sun, and its radius is about 5% bigger than that of Jupiter. Gravitational forces are barely strong enough to maintain the thermonuclear reaction in the star's interior. That is why the surface temperature is just 2,900 Kelvin, or roughly 2,630 degrees Celsius. As is the case for all red dwarfs, Teegarden star's habitable zone is comparatively narrow and located very close to it. Back in 2019, 2 exoplanets were detected in its system after continuous observations of the star's proper motion. Interestingly, one of them lies beyond the star's habitable zone and the other within. The outer planet, dubbed Teegarden C, follows an almost ideal circular orbit around the system's center. With the orbit's radius 0.045 astronomical units, it is completed every 11.5 days. It is presumably a rocky celestial body with a mass 11% bigger than that of the Earth. Its radius is estimated to be approximately 3.5% bigger than that of our planet. Unfortunately, conditions on Teegarden C's surface are far from hospitable. Due to the low luminosity of its parent star, the object enjoys 63% less energy than what the Earth receives from the Sun. As a result, the planet's surface temperature is gauged at 47 degrees Celsius below zero on average, which is too low for life sustenance, at least in the forms we know it. Still, the chance of there being vast oceans of salty water concealed under a thick layer of ice on Teegarden C, as is the case with Jupiter's satellites for instance, shouldn't be ruled out. As for the inner planet, it is dubbed Teegarden B. It is actually this planet that is the most Earth-like object of all those discovered to date. Its ESI is 0.95, which is just 0.05 less than the standard ideal value of our Earth. This celestial body lies 0.025 astronomical units away from its star, and it takes it roughly 5 days to complete a full orbit around it. By following a practically circular orbit, the exoplanet is constantly in its star's habitable zone, and it receives 15% more radiation from it than the Earth from the Sun. According to some estimates, Teegarden B's mass is just 5% more than that of our planet. As for its radius, it differs from that of the Earth by a minuscule ratio, which means that the gravitation value is also quite close to what we're used to on our home planet. This makes it logical to assume that the inner makeup of the exoplanet is highly likely to be similar to that of the Earth. There is a massive metallic core coated in a thick layer of molten silicate mantle reckoned to be at the center of the planet. The celestial object's outer part is covered with a relatively thin crust of solidified rocks. Mathematical modeling shows that the average temperature of Teegarden B is 28 degrees Celsius, which is 14 degrees more than that of the Earth. This means that conditions on its surface allow the planet to have and retain an ocean of liquid water, and the planet's temperature profile is potentially favorable for most microorganisms. Even though Teegarden B is quite massive and is capable of retaining a comparatively dense atmosphere, the radial velocities method, which is used for exoplanets detection, is quite inadequate for obtaining any information about the atmosphere's composition. But it should be borne in mind that a planet's temperature profile directly depends on its atmosphere's composition. For example, a dense atmosphere with a high percentage of methane and carbon dioxide will cause a strong greenhouse effect. Dense clouds of water vapor, meanwhile, will on the contrary reflect sun rays, which reduces temperatures. We should also remember that no matter how optimistic the parameters of this fascinating celestial body might appear, it is not entirely flawless. Being in close proximity to its parent star, it seems that Teegarden B is always facing it with one and the same side, which causes sharp temperature differences between the day side and the shadow side. As I've already mentioned, Teegarden's star is a red dwarf, and this class demonstrates a tendency to suddenly flare up. The amplitude of fluctuations in its luminosity may reach 30%, which greatly affects the planets located close by. Still, the chances of Teegarden B's capability of sustaining life are high. Biological creatures often demonstrate incredible viability, and their ability to adapt can't but amaze. For example, the ocean could serve as protection against lethal radiation and sharp temperature fluctuations. Its upper layer is potentially capable of absorbing cosmic radiation, while its currents could dissipate temperature contrasts. For all we know, as time goes by, primitive organisms might evolve in the warm depths saturated with energy and microelements. Just a tiny chance is sometimes enough for life to develop into something bigger. It can hardly be disputed that life is one of the most amazing, complex, and mysterious phenomena in the universe. Despite the fact that we've been studying it for thousands of years, many important questions about it still remain unanswered, and the greatest among them is how widespread is biological life beyond our planet. At this point, we cannot yet say with a satisfying degree of certainty whether the Earth's biosphere is a unique phenomenon, or whether it has emerged as a natural and logical result of continuous evolution. It is hardly surprising that the search for life beyond Earth is one of the most important fields in science. And in order to identify the most promising celestial bodies in this respect, the so-called Earth Similarity Index, or ESI, is used. It is based on two main parameters: the level of gravity on the surface of a celestial body and its equilibrium temperature. It is these parameters, according to scientists, that determine how much the other world can be similar to Earth and how favorable the conditions on its surface are for hypothetical life. The undeniable advantage of the ESI is its simplicity, because when an exoplanet is discovered, you can usually determine its approximate orbit, mass and size, and this information is just enough to calculate the basic parameters of the index. However, for all its appeal, it does not take into account many factors critical for sustaining life. Therefore, we will allow ourselves to be as presumptuous as to formulate our own evaluation system. taking the ESI as the basis and supplementing it with several important parameters. The activity of the parent star can be singled out as one of them. It is known that frequent flares and stellar matter ejections, characteristic of red dwarfs, can adversely affect the stability of the atmosphere and radiation background of the nearest exoplanets. Nevertheless, red dwarfs are considered more favorable than large stars, like Sirius or Vega, because the lifespan of giant stars is too short and the radiation is too destructive, leaving no chance for potential life to develop. The most favorable ones are orange and yellow dwarfs, including our Sun. The probability of tidal locking is another significant factor to be reckoned with. This probability depends on the distance between an exoplanet and its star. Celestial bodies located too close to their stars permanently face them with one side only. As a consequence, there is a large temperature difference between their day and night hemispheres. Too great a distance from the source of heat and light puts the planet outside the habitable zone, which drastically reduces the chances of the genesis of life. It is also necessary to consider the type and chemical composition of a given exoplanet, because in order to develop, hypothetical life requires a certain set of chemical elements in combination with characteristic relief. Such conditions can be seen on rocky, terrestrial-type planets or super-Earths. Mini-Neptunes, meanwhile, do not have solid surfaces, and ocean planets are deficient in many elements. Thus, the set of parameters we have specified allows us to comprehensively assess how favorable the conditions on a given exoplanet are for hypothetical life. For example, in a scheme like this, the Earth looks extremely attractive against these parameters, being the natural benchmark for other objects. At the same time, Mars, although it has the highest similarity index to our planet in the entire solar system, has a number of obvious disadvantages. It is too cold, too low mass, and demonstrates a significant water deficit. Venus, on the other hand, despite appearing very similar to Earth on the face of it, is too hot because of the strong greenhouse effect. And although most of its parameters are in the green zone, the extremely high temperature is a critical disadvantage of the planet, effectively cancelling out all its advantages. Thus, there are no planets within the solar system sufficiently similar to Earth to be considered favorable for life. However, beyond its boundaries, more than 5,000 other worlds orbiting distant stars have already been discovered, and in many respects, some of them can be considered similar to our planet. One of these objects, closest to us, is an exoplanet known as Gliese 1002b. It is located just 15.2 light-years from our planet. It was discovered in 2022 using the radial velocity method. This method is effective for finding relatively close exoplanets and involves capturing subtle fluctuations of the parent star caused by the movement of space objects around it. The exoplanet is located near a small and dim red dwarf known as Gliese 1002. Its radius is only 14% that of the Sun, and its mass is 8 times smaller than that of our star. Given that Gliese 1002 has a surface temperature of just 3000 Kelvin, or about 2730 degrees Celsius, it is not surprising that its luminosity is extremely weak. It's about 700 times weaker than the Sun's. Observations also show that the object is quite serene, which is unusual for stars of this class. Due to the low luminosity of this red dwarf, its habitable zone has an extremely small radius and width. However, the object Gliese 1002b is located near its outer edge and can be considered potentially habitable. According to observations, this celestial body completes a full orbit around the center of its system roughly every 10 Earth days. Consequently, The average radius of its orbit is clearly very small and is about 0.046 astronomical units. It is assumed that because of the extreme proximity to the parent star, the exoplanet is likely to be tidally locked, facing it with one side at all times. Calculations show that the celestial body receives 1.5 times less energy from its star than Earth does from the Sun, and its average surface temperature could be approximately 230 Kelvin or 43 degrees Celsius below zero. Incidentally, it is slightly warmer than Mars. Given tidal locking and a possible greenhouse effect, this means that liquid water could be found on the exoplanet's surface, and thus there may be conditions for sustaining life. At least some terrestrial organisms are able to survive in such conditions. Calculations also show that the mass of Gliese 1002b is 8% greater than that of our planet, and the radius exceeds the Earth's radius by only 3%. Using the data, it is not difficult to determine the acceleration of freefall on the surface of the celestial body. It practically does not differ from the value we're used to. Thus, the combination of all known factors suggests that Gliese 1002b is a rocky planet, most of which is covered with ice. Due to its size, which is very near to that of the Earth, it has a rather high ESI of 0.86, and in our scheme this object would look like this. At the same time, modeling of the planet's climate shows that its illuminated hemisphere can receive enough energy to support an ocean of liquid water, with archipelagos of islands or even fully fledged continents. Also, tidal deformations caused by the nearby star warm up the planet's interior, so the existence of an ocean hidden under the ice, even on its night side, shouldn't be ruled out. Incidentally, Gliese 1002b is not the only planet in the system. It was discovered alongside another object dubbed Gliese 1002c, which is located a little further away, namely at a distance of 0.074 astronomical units from the center. A full annual rotation takes this exoplanet 21 days, and its mass exceeds the Earth's by about 36%. The object receives 4 times less energy from the parent star than our planet does from the Sun, so the temperature on its surface is quite low, just about 182 Kelvin or 91 degrees Celsius below zero. If we use the previously developed scheme, then this exoplanet will look like this. It can be assumed that the conditions on the surface of Gliese 1002c are close to those observed on the satellites of Jupiter or Saturn. Increased volcanic activity caused by the planet's high mass could lead to the formation of a hidden ocean, with warm and salty water rich in many chemical compounds. Hypothetically, life could also develop in such conditions, possibly in highly unusual and unexpected forms. Of course, among the great variety of known exoplanets, much warmer and more favorable worlds can be found. Such, for example, is the planet K2-72e, located 217 light-years away. It orbits a small red dwarf, about 4 times less massive than our star. Its radius is 0.33 of the solar radius, and its temperature is relatively low, reaching 3,360 Kelvin or about 3,100 degrees Celsius. Observations made by the Kepler orbiting telescope showed that the exoplanet crosses the disk of the parent star every 24 days. This means that the radius of its orbit is very small and is about 0.1 astronomical units, which implies that the celestial body is located within the habitable zone and can be considered potentially favorable for harboring life. According to the received data, it is also suggested that K2-72e may be tidally locked or in orbital resonance like Mercury. Despite the star's low luminosity, the exoplanet receives 11% more energy than Earth does from the Sun. Assuming that the atmosphere of K2-72e is similar to Earth's, the average temperature on its surface should be about 295 Kelvin or 22 degrees Celsius above zero, which is slightly warmer than on our planet. At the same time, it is worth remembering that if the celestial body is tidally locked, there is a high probability of extreme temperature variations between the day and night hemispheres. In addition to this, it must be taken into account that its parent star, like most other red dwarfs, is erratic and is often observed to flare up and emit great amounts of stellar matter, which can be detrimental to the atmosphere and surface of nearby space objects. Calculations show that K2-72e is 29% larger in diameter than the Earth and is about 2.2 times more massive. Knowing this, we can calculate the level of gravity on the surface of the celestial body. It is about 32% higher than we're used to. Thus, with all the known data taken into account, we can assume that this exoplanet is more likely than not a rocky super-Earth, where liquid water and a dense atmosphere can be found. Its Earth similarity index is quite high and is 0.87, and in our scheme this object will look as follows. Planets of this type are expected to have a wide variety of chemical elements, and their relief should be smooth and favorable for the origin of life. Undoubtedly, the frequent flares of a nearby star pose a tangible threat to the atmosphere, but a powerful magnetic field will hypothetically deflect stellar wind particles, and the oceans will protect their inhabitants from this destructive radiation. In this case, we can assume that on K2-72e, it is possible to observe incredible auroras, by far more impressive ones than on our planet. As for the hypothetical biosphere that could develop on such a planet, it would likely be markedly different from Earth's. A different spectrum of incident light might force local plants to use alternative substances for photosynthesis, so their leaves would likely be purple or reddish in color. In addition, excessive radiation hazards may be an obstacle for life forms to venture on land. Alternatively, it may lead to the evolutionary formation of defense adaptations, such as thick skin or specific cellular structures. Similar features are known to manifest themselves in some terrestrial organisms, such as tardigrades, archaea, and some fungi. Meanwhile, in addition to this planet, so attractive in many respects, 3 other planets have been discovered in the system. 2 of them, dubbed K2-72b and K2-72c, are located very close to the parent star and are slightly larger than our Earth. It is assumed that due to the emissions and stellar wind of the nearby star, they are devoid of any atmosphere and are similar to Mercury. The third planet, K2-72d, is estimated to be comparable in size to Earth, and its orbit has a radius of about 0.08 astronomical units. It completes a full orbit around the center of the system approximately every 15 days and is located near the inner edge of the habitable zone. Because of its high temperature, conditions on its surface are likely to be close to conditions on Venus, and the probability of the genesis of life is extremely low. In any case, research on this system is still going on, which means we have much to learn about it in the future. Incidentally, all the objects we have looked at here are similar in size to the Earth. However, life is known to be able to adapt to a wide variety of conditions, including high gravity, which is inevitable on massive planets. If we travel about 1,800 light-years away from the solar system, we can find a yellow dwarf with parameters very similar to those of our Sun. It's called Kepler 452, and it's a main sequence star, just 3.7% more massive and 11% larger than the Sun. In 2015, an extremely remarkable exoplanet named Kepler 452b was discovered near this star using the transit method. high-precision measurements allowed us to calculate that it's located at a distance of 1.04 astronomical units from the center of the system and completes a full annual rotation every 385 days. This location renders the probability of tidal locking of the celestial body extremely low, which is undoubtedly a favorable factor. According to the available data, the object Kepler 452b is about 5 times more massive than our planet, and its radius is about 1.5 times bigger than Earth's. This means that the acceleration of freefall on the surface of the celestial body is 2.2 times higher than we're used to. Such a high level of gravity likely helps the planet retain a dense atmosphere and also smooths out its relief, which could lead to the formation of numerous shallow and warm seas. Such conditions are thought to be the most favorable for the potential origin of life, but gravity this high would be extremely uncomfortable for humans. It is also known that Kepler 452b receives 10% more energy from its parent star than Earth does from the Sun and is in its habitable zone. Calculations show that the average surface temperature of the object is about 300 Kelvin or 27 degrees Celsius above zero, which is 11 degrees more than on our planet. This means that the climate of Kepler 452b may be close to that of the Earth's Mesozoic. However, with a certain composition of the atmosphere, this temperature may be dangerous and may lead to the acceleration of the irreversible greenhouse effect to the point of complete vaporization of the oceans. According to some hypotheses, it was a process of this kind that radically changed Venus several billion years ago. With all the known factors combined, we can assume that Kepler 452b is most likely a rocky super-Earth, rich in a wide variety of elements and minerals. It is believed that because of the increased content of radioactive elements, a planet of this type should exhibit increased volcanic and tectonic activity, and its high gravity should prevent the formation of extremely high mountains and deep chasms. At the same time, the ratio of land to ocean on the surface of Kepler 452b should be different from that on the Earth. Consequently, chances are that this exoplanet may turn out to be a boundless ocean dotted with archipelagos. If we leave the abstract figures for a moment and try to imagine what life might look like on this amazing planet, so similar to Earth and yet so different from it in so many ways, a truly fantastic sight will unfold before our eyes. The probable abundance of shallow, warm seas allows us to expect a great variety of aquatic life forms, from the smallest to the most impressive. As for land, there are likely to be stocky trees with thick trunks and stalky herbaceous plants. Because the spectrum of the parent star in this system is close to that of the Sun, the color of the photosynthetic parts of local plants is likely to be familiar to us, green or bluish. We can also expect a variety of small animals with sturdy bones and strong muscles. Another course evolution might take is creatures with an external skeleton, like terrestrial arthropods. As for flying creatures, the opinions of exobiologists are divided. Some believe that high gravity will be an insurmountable obstacle to flight, while others suggest that the high density of the atmosphere will be the decisive favorable factor in this matter. In any case, we still have many years of research ahead of us before we can say with any certainty that this planet is indeed suitable for life. We keep searching for life high and low on the planets of the solar system and beyond. We may encounter it in familiar forms or in exotic forms that are hard to imagine. However, the constant development of technology inevitably brings us closer to the moment when it will be possible to answer one of the main questions of modern science with certainty. Are we alone in the universe? And let's keep in touch.